Hi. We are in logic design course. There are two main sections within this course. One of them is combination circuits. The other one is the sequential circuits. So now we are starting that new section, sequential circuits. Sequential circuit has got memory elements in it. So the first, in this chapter, chapter 6, we will be examining these memory elements. So how we are going to examine it? We are going to examine the sequential circuits first. This is the general structure of a sequential circuit. We will be examining this. And then we will be seeing the model, three different models to represent a sequential circuit. And then we are going to come to the memory elements. Memory elements are in two different groups. One of them is called latch memory elements. The other one is edge-triggered memory elements. The other name for edge-triggered memory elements are flip-flops. So let's start from the general structure of a sequential circuit. So let's move to open board from here, escape, drop it down, put the open board in, come to OK, open board, OK. Now let me clear it while explaining it. So we've got here a box. This box is considered as a sequential circuit. Here you are. This is a sequential circuit for you. This is the input of it, input variables, and these are the output variables. So if you go inside, there's a combinational part, and there are memory elements in it. So we have seen the combinational circuits before, so we know what it is. Just remind you what it is. If the inputs are known of a combinational circuit, for these combinational circuits, these are the input variables, then the output is determined uniquely. So if you know the input, you can tell what the output is for the combinational circuit. But if it is a sequential circuit, these input variables are not enough to say what the output is. So you need additional variables. We represent these additional variables represent the information in the memory. So these variables represent memory elements. So here you are. These are the memory elements we have got. In this circuit, we've got our memory elements. Memory elements, that means R number of variables additional to these input variables. So we said input variables are not enough to determine what the output is. We need additional variables. These additional variables are these variables. These variables are called state variables. There are R state variables. That means R memory elements. So each state variable represented with a memory element. You see here, Rth memory element, small yr. First memory element, small y1. So if you got just one memory element, that means you got one state variable. If you got one state variable, there are two states. If this variable is 0, this variable could have the value 0 or 1. So there are two states here. So in order to separate two states from each other, you need just one variable. If you got two variables, y1 and y2, so there are 1, 0, 0, 0, 1, 1, 0, 1, 1. Altogether, you got that 2 to the power 2, 4 different information that you can keep, or 4 different states that you can represent by using two state variables. So what is the relation then when if you generalize it? If you got r number of state variables, in other words, if you've got r number of state variables, then you can represent or separate 2 to the power r number of states from each other by using these state variables. Okay. So I just introduced you what this state variable is. And this additional state variable, why do we need that? If I explain this on an example, you're going to understand it much better. So you got, let me explain to you. Okay, just put it back again. So there is a box here. This box is a parallelism. Oh, okay. Parallelism. So if you remember, parallelism has got two numbers a and b, and at the output you're going to get a plus b. When it is parallel, these a and b numbers, all the bits of these two numbers a and b are applied at the same time. So you got 8 wires connected to the input. Okay. The one that we're going to examine here is not the parallel ladder, but it is serial ladder. When it is serial ladder, you are not going to apply these two numbers all the bits at the same times. You are applying this least significant bits first, and then the other bits, and the other bits, and the other bits, not all the bits. So in a sequence, we are applying these numbers inputs. So you've got 12 here, x1 representing x1 variable, and number 14 representing x2, represented by x2 variable. So if I write those numbers here, so 0, 1, 1, 0, 0 for 12, and 0, 1, 1, 1, 0 for 14. So if I am going to do this addition operation by hand, so I'm going to say that 0 plus 0 gives some 0, and the carry is 0. So this carry for the first least significant bit, it's going to be 0, of course. So summation 0, that's the carry. So when you add those three up, you're going to get sum 1 and carry 0. So 0, 1 plus 1 gives you 2. Put 0 here, carry is 1. So 1, 1, 1 gives you 3, that is 1, 1. This significant bit 1 here, and the carry is here. Add them up, you get it 1. So this is 26. This is how we have done it by hand. So if we compare the inputs and outputs at that stage now, we are going to see here input 0, 0. In here, input is also 0, 0. But the output is 1, 1 case and 0 for the other case. This tells us this is not a combinational circuit, this serial ladder. Why is that? Because for the same input, you are getting different outputs. In a combinational circuit, we said if you know the inputs, you can uniquely determine what the output is. So this is not a serial ladder, is not a combination circuit. So you could do, there is an alternative to this one as well. For example, this 1 input here and another 1 input here. If you look at the outputs of these 1 inputs, they are different. So another example for you that inputs do not determine the output uniquely. So how I am going to separate those two outputs? You've got to know the carry information. If you look at the carry information here, make it black. For this red one, the carry is 1 here, but the carry is 0 here. So if you know the 0, 0 input and the carry information, then you can uniquely determine what the output is. If we look at these green ones, the inputs are the same, but the carry variable is changing. 0 in this case and 1 in this case. That's why the output is different. So the output is uniquely determined if you know the input plus the carry information or state variable. So that is carry. In practice, what we call that. In mathematical sense, this is state variable. In circuit level, this is memory element. How we need these memory elements, I'll tell you. When you're adding those three things here, you get the 0 here and that 0 as carry. You've got to keep that carry in your memory for the next bits to come. So you are keeping that information in your memory for the next bits to come. So it is going to be repeated like that. So that memory comes in. So I am keeping that carry information in my memory. Since I carry value could be either 0 or 1, just one variable is enough for me. So I can say that within this circuit, there must be a memory element if it is serial ladder. So this is a practical information for you to understand what state variable and memory element relation. So let's generalize this to how the brain works. So I can give you an explanation for that, saying that assume that there are two persons and there is a teacher. Let's make it, oh, okay, you can make it the same, and the teacher here. So if those two people, they know some information about logic circuit. This is, let's say, A person, and this is Aisha, this is Fatma. They've got different information in their mind when they come to class. So this teacher tells you something, that's that information. So this teacher here is going to teach you this. This is the input. And there is a state A is the Aisha memory information, and this is state F memory information for Fatma. So if this input comes, Aisha is going to have the new information in her mind, and Fatma is going to have a new information in her mind. These informations are not going to be the same because Aisha, before this new information come in, had some information about logic, and the other one has no information about logic circuits. So that means after they receive this information, input information, they are going to be in different level for understanding the course. So these are the new states, new state, let's say, call it, or new memory, and new memory for Fatma. So how we are going to represent it in here, you see that memory element has got the small y's here. If you got the small y's, plus you apply the input here, as you see, a combination circuit works. Some new information comes to the input to the memory elements. So this new information is going to transfer what they've got their mind is going to be their new information or new state, which is this. So we represent this new information here as next state. Next state. These small y's represent present state. Present state. So let me explain now. Present state is the Ch6 state before the information comes in, and Fatma present state, which is F, is the memory of Fatma when that input information comes in. But when this input information comes in, the memory of Aisha is going to be the next state here. So this is this one. So these are the small y's, y1, yr, y1, yr. So that means present state. When that information comes in from the teacher, so Aisha's information in her memory is going to be the next state. So this is next state. Let's make it green. Next state. We represent it with capital Y, and this is next state for Fatma. This is capital Y. You see now how it works. So when consider that teacher said something else, the new input. After the new input, this memory elements input are going to change. Your new memory is going to change. So present state, next state, present state, next state, it goes like that. You might say that present state is the state before that input information comes in. Next state is the state after this input information came in. So we can categorize the sequential circuits in two groups. One of them is called synchronous sequential circuits. The other one is asynchronous sequential circuits. The difference is this: in general, I can tell you. If you look at these memory elements, they are all connected together, and one input of these memory elements is called clock input. This is a central clock. So this is a common clock for all the memory elements. If it is like that, we call it synchronous sequential circuit. Why we call it synchronous? Because they work depending on that clock pulse input. So just remind you, maybe you didn't know the relation, but you might heard of that. In computers, we've got central processing units, CPUs. The CPU's clock frequency is 3 gigahertz nowadays, is common one. You might heard of this. So this is 3 gigahertz clock signal is this signal. What it tells, that's 3 gigahertz, that means within 1 second these memory elements works 3 billion times in 1 second. So how fast is it? Higher that frequency is, that means the central processing unit does more job within the same time interval. So higher the speed, better the processing power. So when these computers came in, that speed was in the range of megahertz, a few megahertz, so it was quite slow. But nowadays it is in the range of gigahertz. So that is end of this video then.